All right, hey everybody. This is a brief tutorial that I'm going to do on finding isoelectric points in short peptides. And I just have one example that I'm going to share with you here today, but I have broken the video down into some segments based on kind of the topics that we're going to cover as we review this. So feel free to skip around in the table of contents here. The problem that I want to share with you here is just a classic issue where we've got a peptide. This is actually a pretty long peptide. It's 9 amino acids long, and we need to find the isoelectric point of that peptide. And this can seem like kind of a daunting task because if you felt like you had to draw the entire structure out, it would probably be pretty time consuming. But what I'm going to try to show you in this tutorial is some shortcuts that we can take to really identify the parts of the structure that are important and kind of avoid drawing a structure of something this long if we can help it, but still get to the answer in the end. So one of the things that I want to point out right away is just reviewing the definition of an isoelectric point, right? So we should remember that an isoelectric point is basically a pH. So an isoelectric point, we usually call it a PI, we abbreviate it that way. It's the pH at which the neutrally charged structure is most dominant. And so that's something that we need to kind of examine the pH scale for and assess the charge on our peptide as we kind of sweep through that. There will be a point where the most dominant structure that we see in solution is going to be the structure where all the charges balance out. And so we're gonna have to do some investigation to determine where that is. A couple things right away to identify about this that will hopefully make our job a little easier. And the first thing I want to review is just the general structure of peptides and what we end up kind of switching up when we transition from talking about individual amino acids into peptides here. So I'm going to draw 2 amino acids, just generic structures of amino acids on my screen here. And my goal here is going to be to bind them together as part of an amino acid chain and a short peptide here. So there's a few common structures that are always around when we're talking about amino acids. We have the carboxyl group, which is on the right-hand side of the structures, the way I've drawn them here. That's an ionizable group and can lose protons and potentially become charged. And so that's something we want to watch out for if that appears in our structure anymore. And the amino terminus, which I'm now underlining here on our structure, that's also an ionizable group. So every amino acid by itself has 2 ionizable groups on it at least. And then we have the R group, which is often referred to as a side chain. And that is something that might have an ionizable group or not, we're not sure, right? So if I join these things together in a peptide bond, and I make a dipeptide out of these 2, what we're going to end up doing is basically doing a condensation reaction. So we do a nucleophilic substitution on one of these carbonyl carbons in the structure, and we're going to end up losing an alcohol group. And I'm also just going to rewrite this and rearrange it a bit here on this structure. Oops, I'll go to a different color here. And we're going to lose a hydrogen and off of one and a hydroxyl group off of the other. And the peptide bond that we form is actually going to stick our protein structure together just like so, right? And the main thing I want to identify here is that we still have an ionizable group, this amino group here on the N terminus of our new little peptide. And we also have an ionizable carboxyl group on this end. But the stuff that used to be in the middle here, we used to have 2 ionizable groups that were present on the individual amino acids. These are now missing. And amides, like peptide bonds, are not ionizable, at least on a reasonable pH scale. And so we're not going to consider those, right? So that's going to play into some shortcuts we can take. If I draw out the structure of this peptide that I've given us, it's all different amino acids here. So I'm just going to draw this in a slightly expanded form down on the bottom of the slide. And then we'll consider each of these amino acids individually here. And if I do that, I have a number of different structures to consider with this. Okay, but the first thing I can identify is that just like in that little dipeptide that I drew up above, we're also on this one going to have a little N terminus here that has an ionizable NH2 or NH3 plus group on it, right? And that's the charge on that is gonna depend on its pH, the pH of the solution that it's in. Likewise, we're gonna have a C terminus that has a carboxyl group on it. So those are two ionizable groups I can identify right away. Everything else in the middle here, if we consider these individual connections between amino acids, right, and so on, those are all going to be condensed into peptide bonds and their ionizable groups are gone. So we don't have to consider anything going on with the linkages between those amino acids. What we do potentially have to consider is the actual side chains on these amino acids. And this is where we get out our reference table. Most reference tables for amino acids will have a name and maybe some other properties. But if we're looking down in the columns associated with each of these, there's probably going to be 3 columns representing different pKa values. And so each of these represents the sort of turning point in the pH scale where we reach a 50-50 mixture of a protonated and deprotonated state. Usually pK1 on these tables refers to the carboxyl group that's part of the amino acid backbone. pK2 is that NH2 or NH3 plus group. And then pKr is the side chain. And so sometimes when you look at an amino acid on the chart, for instance, the first one here, methionine, right? We're probably going to see a value for methionine. I'm just going to write in the values here, something around 2 for the pKa associated with that carboxyl group that's part of the backbone. For methionine, we have a value of 9.21 for the second one, and usually values for the backbone amine group are also somewhere around 9. That's pretty typical. But if we look on the chart, there won't be anything in the category here for the side chain. All right, and that is in contrast to something like lysine, which we have on the other end of our protein. We've got another value. If I look this up in the table, it's very close to 2, right? So these don't vary by a whole lot. And lysine also has something very close to 9, 8.95 for the second pKa. But lysine on the chart has a pKr that's actually listed, all right? And that's what tells you right there that you have an ionizable group in your side chain. So what you can often do to really simplify this is just go down your reference page, take a look, and if you see a pKr, you know that that's another ionizable group you're going to have to worry about. We can write that down, that value, when we're analyzing the structure. And if not, we're just going to ignore it in the structure here. So going through that process, I have methionine, like I said, doesn't have an ionizable group. If I check my reference page, actually none of these first 4 have anything listed under their R groups. And we don't have to worry about the backbone atoms because they're part of a peptide bond now. Tyrosine has something, so I'll leave that for the moment. But leucine and proline also do not. So this is where we're sitting here. We've got 3 amino acids in our protein chain that have ionizable groups that we're going to have to consider. And that gives us a total of 5 total ionizable groups to look at, if you count the N and C termini as well. So the next thing we want to do is just find the pKa's associated with these groups, all right? And it will also be helpful if we can just get a sense for what kind of group we're talking about here. So this is why learning the relationship between the structures and the names of the amino acids is also something that can help speed you along here, all right? So for starters, we've already highlighted that the N and C termini of this peptide have an amino group and a carboxyl group respectively. So I'm going to look in my table and I'm going to get the exact values for the pKa's associated with that. So for our amino terminus, this is going to be the pK1 value, or sorry, pK2 value that we look up. And for our carboxyl terminus, this is going to be the pK1 that's listed in the table. All right, so we got to make sure we're picking the right values here. So for methionine, just like I mentioned before, it has a pK2 listed on the table of 9.21. And so that's the value that we're going to put down as one we have to consider. The carboxyl group, the backbone carboxyl of lysine, like we can see on the chart there, has a pK1 of 2.18. So that's also another value we need to write down. And now for the rest of these, for the three that are in the middle, I'm going to look at the R groups. So we already got lysine. Lysine has a pKr of 10.53. That's the group that we're going to need to worry about. And the other thing that's going to be really useful to know is that lysine has a side chain where its ionizable group is an NH2 or NH3 plus, an amino group, right? So that's another piece of useful information. Okay. Moving down the list, going backwards a little bit, I'm going to look at aspartate first, or next in our section here. This has a pKr of 3.65. And it's also important to know that this one has a carboxyl group on it. So just examining the structure will show you that if you look at the side chain. Okay. And then finally, we have tyrosine. Tyrosine is sort of a unique one because its structure isn't an amino group or a carboxyl group on its side chain. In fact, tyrosine has sort of a side chain where we have an aromatic ring, and then we have an OH attached to that. And it turns out that this proton here is actually kind of acidic. And if the pH gets high enough, then the dominant structure will shift so that that protein, that proton there is lost. And we're going to end up with a negative charge. All right. So just getting those numbers is most of the work. And now we need to go ahead and solve this by kind of organizing these and determining where that isoelectric point is going to be. So next in my solution, I am going to move ahead and go ahead and just draw a pH scale. I find this to be a really helpful visual aid for myself. You can probably do this in your head, but it's helpful to just have everything laid out, right? So on this line, I'm going to have pH increasing going from left to right. And what I want to mark out on this line are the turning points that I need to be aware of in this structure. So those are going to be my pKa's. So I'm just going to label the pKa's on this number line here, just going from smallest to largest. So I just have to arrange these properly here. And the next, so there's going to be a big gap here, but the next one is 9.21. And then we've got 10.07. And then finally 10.53. And I just want to leave a little bit of space between each one. I don't need to draw this to scale, but these are the turning points where a particular group is going to be, if we're at that pH, is going to be 50-50 in terms of its protonated slash deprotonated ratio. All right. So what I will recommend is that we start over on the far left side of the scale. And let's just remember that when we're at a really low pH, we have a lot of hydrogen ions around in our solution. And that's just kind of a nice intuitive way of reminding ourselves that as we get further towards the left, more and more of our groups are going to be protonated. There's more hydrogen ions in solution, so it's easier to put protons on them, right? And if we're far to the left of everything that would represent a turning point in our structure, if we're all the way on the left side here, all of those groups are going to be protonated, all the groups that we just identified. So the challenge is to figure out what the net charge is going to be. And this is where your structural knowledge has to come into play. So starting with our N terminus here, we talked about how this N terminus is an amino group. And when amino groups are protonated, they look like what I've drawn here initially. All right, they have a positive charge. The protonated form of an amine is having an extra hydrogen attached, which gives the group a positive charge. So we're going to mark that as a positive charge. I'm just trying to find the net charge at this really low pH. And this is how we're starting. Tyrosine has this structure as we discussed. That's neutral when it's protonated. And if we lose that little proton that I have underlined, it will get a negative charge at the end of of that process. So a protonated form is neutrally charged, right? So this one has nothing that we're adding to our total. Carboxyl groups, like this COOH on aspartate, also are neutral when protonated. Here again with lysine, as we move to the right here, lysine has an amino group as well. So its structure is actually going to look like this. It'll be an NH3+. That gives us a positive charge overall. And then finally, we have one last carboxyl group, which is our C terminus, right? And that one is also going to be neutral because protonated carboxyl groups are always neutral. So we just add all of these numbers up, and the net charge on this peptide for this entire region, actually, of our pH scale here to the far left, our dominant structure in solution until we get to that 2.18 mark is going to look like the structure that we've assessed in red up above there, right? And it's going to have a net charge of +2 if we add up all of those groups and get the net charge that way, okay? Now, once we reach 2.18, this is the magic number for this C-terminal carboxyl group. The pKa corresponds to that group. That is the point where if we're at that pH, if we're sitting right on 2.18, we'll have a 50-50 mix of the group that I initially drew up there and the deprotonated form that has a negative charge. So there's a balancing point that we can identify there with that pH. But if we move any further to the right on this scale, we're going to transition to a point where this deprotonated form of our carboxyl is dominant. So we're actually going to lose 1 from our net charge in this region of the pH scale because we will have transitioned from a neutral group over there to a negatively charged group. Okay, but everything else is going to stay the same until we reach our second pKa. And once we pass that one, as we continue going further to the right, our second R group here that has our second carboxyl that we can identify, this one is going to transition to being negatively charged as well. So I can get rid of our neutral charge that we identified from it, and this one is going to have a negative charge. And I guess I can do that for carboxyl on the C terminus as well. This is what that structure will look like now. And now if we add up all the structures, the different charges here, we have a neutral, 2 negatives, and 2 positives. So that all cancels out. And for this entire region here, our protein is going to be neutrally charged, right? Okay, so then we keep going. And we can kind of start to identify a pattern here, right? Every time we move across one of these dividing lines, which are represented by the pKa's, we're stepping down in charge by 1. So this time, it's actually going to be the N terminus that loses its proton, and that will change it from being positively charged to a neutrally charged NH2 group. And so that will become neutral here, but that drops the net charge by 1 again. So we're going to end up with a -1 here for this region. And I can continue to work on here. I'm going to clean up my slide a little bit, but the pattern is going to continue. And what we're going to end up with is stepping down by 1 charge value each time we do this, this transition over a pKa. So the rest of the graph, you can kind of do this for yourself on your own to convince yourself that this is how it would work. We'll have 2 additional regions here that we won't really go into exhaustive detail with. And that's what our charge landscape is going to look like in different parts of our pH scale. So now the question is, where is our isoelectric point? We've identified all the net charges at all the different regions in this pH scale. And the place that we're interested in is the place at which the neutrally charged structure is most dominant. So if the pKa's are the transition points, what we want here is the position right in the middle of the 2 pKa's that serve as sort of transition points into that neutral structure, right, above and below it. So we want the position that we're sort of highlighting there with the dotted line. This is the position that is where we'll have the most of that neutral species hanging out. So we take these two pKa's, the ones that are on either side of our neutrally charged region, and we find the exact midpoint between them. And the easiest way to do that is just to average. So we're going to take those two pKa's and take them over 2. And the midpoint between them is going to be the isoelectric point, which is going to come out to be 6.43 in this case. And that would be our answer, right? So we spent a lot of time explaining the different considerations here, but hopefully we can recognize that doing a problem like this doesn't need to take us all night, right? It just needs to be important that we identify first the ionizable groups, which is what we did on our diagrammed structure here. We got their pKa's, we arranged their pKa's on a pH scale, which we did down here, and then we just picked a region of the scale. I used the very low pH regime down here below our first pKa, and we used that as our starting point, and we calculated the net charge on our structure when everything was protonated. Then we recognize that as we move to the right on our pH scale, we're just stepping down in net charge by 1 each time. So there's a lot of things you can do here to speed up your workflow, and I hope this was helpful to see. All right, that's all I've got for now. Please feel free to review different parts of this if you want to see anything again, but this should be all you need to tackle what amounts to a pretty complex problem, hopefully a little bit faster now. All right, thanks for watching.